Hello and welcome to the second video in the series of how to use Threatray. In this video we will be looking at how to hunt and pivot with the platform, and if you haven't seen the previous video on detection and identification, then I recommend that you do that first, as it provides a lot of background and basics on the platform itself. You will find a link to that video in the description of this video here. So during the first video we looked at one particular sample which was detected as Latrodectus, and we touched on a few hunting and pivoting related points, notably around prevalence and OSINT hunts. And now we'll dive a little bit deeper into this particular malware family and try to understand how we can use hunting and pivoting to get some interesting information related to that family. Now here we start with a more recent Latrodectus sample that we found in our global threat feed to kind of exemplify the hunting and pivoting capabilities in Threatray. In Threatray you can hunt for many different things. You can hunt for behavioral artifacts like an IP address, a domain, file or process names. However, what makes a Threatray quite unique is that you can natively hunt for code the same way you would hunt for an IP address. This is a very easy and also a more holistic way to hunt for similar samples, since many of the typical artifacts that you use for hunting, like a hash or an IP address, they are easily and also frequently changed by attackers. Especially with advanced attackers, you always have a higher level of OPSEC, and often they don't exhibit these types of artifacts in the first place. And in those cases, hunting for code similarities is actually a good and powerful way to discover related samples. So back to our Latrodectus case here, our aim now is, starting with this particular sample, to kind of gain an understanding of what this malware family does, and for that I first need to have a couple of variants to study. So to discover variants, what I can do here is now issue a Retrohunt, and in Threatray you can basically natively hunt for any piece of code and get back a list of code-wise similar samples. And there's one button here on the right hand side for retrohunting. So here, in this case, we are retrohunting for the payload of Latrodectus, which is also identified as Latrodectus. As you can see here, we could also hunt for, let's say, the packed code or some loader code, but we're not really interested in that in the first place. We really want to have different variants of the payload of Latrodectus. So let me click here on this retrohunt, and retrohunt will now hunt through all of the data that you have uploaded in your private Threatray instance, as well as Threatray's global threat feed, which contains 100+ million samples covering cybercrime, APT, C2 frameworks, and so on. As you've seen, this only takes a few seconds, and what we get back is a search view with the results of the query. Now, what you can see on the top here is the distribution of the search results over time, and we can see that we have results here from March all the way to June, mostly distributed between the March, April and May months, and that kind of gives us a bit of an overview of how the distribution over time of these similar samples looks like. Then what we have here is the list of similar samples, and for example, if we look at this one particular case here, we have the analysis where this similar sample or the code of the similar sample appears in, which was originally the sample here that caused the creation of this analysis. It's identified as Latrodectus. It was a dynamic analysis on a Windows 10 machine, and we can also pinpoint the exact place of where we found the similar code, which here is in this process with the given PIT and the base address. At the end, we also indicate the similarity of this piece of code that we found, which is 100%. 100% doesn't mean it's hash equal, it basically just means it's code equal, right? So if we scroll down here through this list and go a little bit further, we have a lot of 100% matches here. Later on, we can also see some 90, 80, 70% matches, right? So that gives us a good set of variants to look at, and we can also pivot to any of those to further inspect the analysis results of these similar samples. Now, on the left-hand side, you can also see statistics over all the search results. Here, most importantly, all of the similar samples were identified as a Latrodectus. So, next up, let's try to look at a couple of these variants and try to figure out what we can learn from the analysis reports of these variants. So let me go back here and pick a couple of diverse ones. Of course, I don't want to pick samples that are exactly the same. I want to have some kind of set of diverse ones. So for example, here is originally a JavaScript file that looks interesting. Then if we go a little bit further, I have some executable here. And even a bit further here, I have some MSI installer, right? That looks like a good set of diverse samples. And if I jump to the JavaScript file here, I can see that we have, again, Latrodectus being detected, of course. If I jump to the full report, I can see a bit the behavioral aspects here, launching C script, which then through MSI exec explorer is then deploying Latrodectus, running here as part of run DLL. So inspecting the reports of the other ones, that's the executable we opened. We can see a much simpler chain here from an executable to this kind of update executable process. And the third one, our MSI installer here. Zooming in, we can see MSI exec, chain of processes to the Explorer to again run DLL, running Latrodectus here. So already with these three kind of variants, we've seen different attack chains, which then ultimately lead to Latrodectus. That's already good and relevant to know how Latrodectus actually is being delivered. And now if we go a little bit further and we inspect the dynamic artifacts, we can also learn some things about what kind of artifacts Latrodectus exhibits. And what is interesting here is actually it has a mutex called Runung, which appears here. And if I switch to the other three analyses, I can see that there's the same Runung mutex being reused here in all of these three cases. Interesting as well is if we inspect here the process memory details, we can see that we always have a process that is being launched out of the roaming directory with update underscore the specific pattern.dll. If we inspect the other ones, we can also see here it's an executable, but the same kind of update pattern. And the third one here as well, we have some particular update pattern. So that kind of gives us a good understanding of some behavioral aspects of Latrodectus, and there's actually an easier way to get to this kind of information. So if we go back here to our initial search with the Retrohunt, we can see on the left-hand side that we create statistics over all of the search results. And here we can also see, for example, if I open the mutex tab here, we have this Runung mutex, which appears in almost all of the samples that we matched here. And if I open the file one here, we can see that we have a lot of matches in this update something.dll. So that gives us a very quick and good understanding of particular behavioral artifacts related to the search we've created here. Now, next up, we actually want to verify whether or not some of these behavioral artifacts are unique to Latrodectus or whether or not they might be shared with other malware families. That, of course, helps us to identify some stable IOCs which we could use for hunting or for detection engineering. And you can hunt for these types of artifacts as well. I can just click here on this Retrohunt, and that issues a new query for this mutex. And we can see that now we have a new set of results over quite a period of time here. That is 100% of them are identified as Latrodectus. We even have some brute ratel in here. So let me filter for that. That might be super interesting to look at. Seems to be some analysis where both of these both brute ratel as Latrodectus have been used. So now let's do the same for our file pattern that we've seen here. So I can click here once again. That will now hunt for both this particular file as well as the mutex. But at the moment I'm just interested in the file, so I'm deselecting the Retrohunt here. And we have seen that we had a couple of patterns here. So actually I just want to wildcard this part of the path. Search again. Let me remove this filter here. And we can see that we have 200 results of samples that were identified as Latrodectus. So with this, we have now actually confirmed that this update pattern as well as the Retrohunt mutex is indeed unique to Latrodectus over a huge data set. So we could now, as a next step, use these kind of information to create the hunting rule for, let's say, if I need to hunt over my infrastructure, or to do detection engineering based on that. All right, so besides retrohunting and hunting for behavioral artifacts, Threatray also includes OSINT Hunt, which is something that we touched on in the previous video. And OSINT Hunt is actually technically the same as Retrohunt. However, the hunting space is reduced to samples that were mentioned in open source intelligence report that we have processed and indexed. And that's a great source for confirmed cases to pivot to, and also actually delivers good additional contextual information on a particular malware family, in this case Latrodectus. So let's check that out as a next step and see what we can do there. So let me go back to our initial sample here. Go to the OSINT Hunt tab, and what we now see here is that we have almost 60 similar samples in this hunt from 23 different OSINT thread reports. And if we navigate through this list, we can see there's a couple of reports from Securonics, a blog post, Alienwald, Aniron, Proofpoint, and so on, right? So that gives me a nice list of samples to pivot to. And actually, if we go towards less similar variants, towards the end here, you can actually see that we have a report from last year here called IST ID gets loaded. If we inspect that one here, that's a report from Walmart back then, and also includes exactly one sample that was mentioned in this report, which is similar to almost 70% to the sample that we're looking at here. So this is a sample that was mentioned 6 months ago by Walmart compared to the sample we're currently looking at. And we can now try to find this particular sample in the thread report to see if we can learn something about what Walmart has reported on. And we represent all 3 hashes here because sometimes some hashes use, some reports use SHA-2, SHA-1 or MD5 hashes. In this particular case, I know that they use the SHA-2 hash. So let's copy that. Open the report here, and I'm just searching for the hash that we copied, which leads me to this section of the report. And here they basically discuss that they had a variant of ISID which loaded this particular sample, which they didn't know anything about prior to actually analyzing it. And in this report, they go a little bit more into the details of this particular file. They talk about the string decryption routine. They actually reverse that, and they extract some strings from this particular sample, and some of these strings will actually be similar to what we found. You can see here the string around roaming, and then update pattern, and as well as this hard-coded mutex, which they found called Runung, the same as we have found when pivoting to a couple of variants and actually hunting for this mutex here. So if we go back now to the analysis here of our initial sample, we can see that the similar sample that was reported by Walmart back then is also identified as Latrodectus here. And we can now pivot to that by clicking on this location link. It will open a new tab and basically lead us to a piece of code here extracted from memory that is directly coming from the sample that Walmart referenced in the blog post. And we can see here that this one is also detected as Latrodectus. So running in this update process here, if we look at the mutex, we can also see this Runung mutex. So with this, we can basically also confirm that this is Latrodectus and kind of mirrors what we have learned so far. If we go to the OSINT Hunt tab of this variant here, we can also see a couple of similar ones that are referenced here 6 months later after the appearance of this sample. And that's actually a very good blog post by Proofpoint back in April of 2024. And they kind of confirmed that the sample that Walmart talked about initially is kind of the first confirmed Latrodectus case, and they then go into more details about how Latrodectus changed over several months. Alright, so now we spent some time hunting and pivoting through many different samples of Latrodectus. We basically started with just a kind of a random sample of Latrodectus. We identified certain stable indicators of compromise based on file patterns, based on this hard-coded Runung mutex, and we were also able to kind of track down our way to an initial sample and again contextual information from Walmart in this case. And this actually covers already the first part of this video. In the next video we will actually look at Latrodectus again and try to reverse engineer and understand a little bit how the variants that we now discovered differ over time. In the previous example around Latrodectus, we were able to hunt a lot by mutex as well as file names. However, such artifacts are not always available, and in this example we will look at an APT where we simply do not find these kind of artifacts. In the first video on detection and identification, we took a closer look at a recent article by Trend Micro on this Earth Predator campaign, where we have quite a nice attack chain that is using Doplugs to then decrypt and load PlugX. So maybe just to recap on that end, in the article they described this attack chain here, where DLL sideloading is being used, starting from an MSI file with a legitimate one-node M executable that sideloads this MSI DLL, which is just a loader which then decrypts and loads from a DAT file on disk PlugX. And we have already analyzed that case in the previous video, and let me just jump to the analysis here. Again, to recap, we have this one-node M executable, which is legitimate. We have the MSI DLL file, which is Doplugs. as well as the memory regions which were decrypted from disk and loaded, which is identified as PlugX. So according to OSINT, PlugX is also an attack tool that is quite frequently used. So what we're interested in here is to actually find a couple of variants of this type of attack, which involves the usage of PlugX. And if we look at the set of dynamic artifacts here, we don't really have much which we could use to hunt for. We could of course try to hunt for the file names, but as we've seen beforehand, these are actually legitimate files and therefore file names. Registry doesn't give us much here, and with the mutexes here we just have some generic stuff. There is one mutex here which might be interesting, so let's hunt for that. And that basically just gives us a couple more samples with this attack chain here. That's not bad, of course, but not really the set of samples that we would like to have to look at. So our only option here is actually hunting by code. And for that, let's again navigate to this memory region here and Retrohunt for the code of this PlugX here. And that should give us a nice list of similar samples. And we can see here on the top end of the list, we have a range of, again, Doplugs and PlugX variants, which are highly similar. This might be interesting to look at. But if we go a little bit deeper, we can see there's some analyses which have PlugX as well as Mustang Panda loader. There's a couple more. There's another one with some good similarity here. So these might be interesting to investigate. So let's open one of these in a new tab. And we can see we are redirected here to process with, again, what kind of looks like DLL sideloading. We have an executable here. Maybe that's, again, a legitimate executable. Then we have a DLL, which here is identified as Mustang Panda loader. And again, some memory region with PlugX. Now, if we check again the files here which were written, we can see that this executable is written, the DLL is written, as well as a DAT file, which kind of looks a bit similar to the Doplugs PlugX variant that we had beforehand. So here, maybe again, we're dealing with some kind of similar behavior. However, this time, it's not Doplugs, it is this Mustang Panda loader. So if we inspect that piece of code a little bit closer, what is always good to check is the OSINT Hunt tab here. And we can see that we have a hash equal mention, meaning that the file that was originally submitted here was mentioned exactly like that in the tweet here. So if we open this tweet here, we can see that this is the hash of the original sample, talking about some IOCs, and related to that, there is a mentioning of Mustang Panda. So there seems to be some sort of relation between what we're looking at and this Mustang Panda group, right? So going back here, we can also see a couple of other open source intelligence reports that were referenced here with a lower percentage score. One of them here from Eclectic IQ about Mustang Panda APT from 2023, so a bit more than a year ago. And we can see a low similarity, but still some similarity, which is also identified here as Mustang Panda loader. And if we pivot to that report over here, we can see that they talk about the Mustang Panda APT group that is using PlugX malware. And if we navigate here to the execution flow of this case here, we can also see that, again, there is some legitimate executable being used. They use DLL hijacking here, which is very similar to sideloading with the PlugX malware loader that then decrypts and loads from, again, a DAT file the actual PlugX malware. So in this case, we probably found a variant of this PlugX malware loader, as they call it. If we go back to our analysis here, we identify that as Mustang Panda loader, which I guess is very close to what it actually is. That is then loading PlugX here in memory, again, very likely over this dat file that was reported here as well. So now with just a few steps and in a few minutes, we were able to kind of discover and pivot to another very interesting sample that is apparently somewhat different, but still has similarities to what we saw beforehand. And that kind of shows the underlying power of such a technology that is based on finding code similarities and being able to hunt for them quickly and efficiently over large amounts of data. Alright, so thank you for watching and see you in the next video. Bye bye.